So welcome back. So in the last class, we discussed mostly planar manipulators. We did inverse kinematics of 2R and 3R planar manipulators. We also did SCARA, that is a three-dimensional robot, a spatial manipulator. So today we'll discuss, that is a 6 degree of freedom industrial robot. So let us start. Mostly all the industrial robots are 6 degrees of freedom and they have almost similar kind of architecture. We'll discuss what are the different types of manipulator that you might see when you actually start working on any of this. So we'll do Yaskawa GP12 robot now. So let us begin. So you see this robot is of kind when you see you have one of the link which is not straightforward. What do I mean? I'll show you here. Normally you see this robot, you see this is one of the robot and for which you can arrange it like this. Whole of the link can go straight like this. Can you see it? You see this joint and this joint and all the joints which comes next can be arranged in a single straight line. Okay, so when it goes like this, it can go perfectly straight parallel to the ground and it can make this kind of motion. Okay, but this is not the case with quite a lot of robot, and your link structure goes little different the way it is there with Yaskawa GP12 robot. This is quite common architecture robot where maybe you have actuators arranged little differently, but the shape of the link is almost the same. Okay, with some dislocation out here. You see, you have first one of the joint which is here, other joint goes here, and finally it comes till rest center point. So effectively the shape of the link is something like this. Okay, so you see a small bit of displacement over here, and also you have a link length that comes here. Got it? So this is what is the shape of that link. So if you talk till wrist center point, till here, so you have first link that is little twisted kind of thing. It is twisted by 90 degree. So you have first axis that is like this, second axis over here, third axis which is over here. Okay, so the shape of the first link is something like this. So you see the architecture goes something like this. So what do you see? The first joint is fine. It can make a motion which is something like this. And the second joint, if that moves, it moves from here. Okay. Third joint can go something like this. Got it? So you see, it is very much similar to a 3R spatial arm with first degree, first, second and the third links arranged like this. Okay, but the shape here is little different. If you see this one very closely, the shape here, you see you have an axis which is over here. Got it? So you have an axis that is here, and this rotates like this. This can rotate like this. Got it? Okay, so overall it intersects somewhere over here. This is the point where it intersects. So the effective shape that goes to this is something like this. From here to here, and it is like this till the wrist center point. Got it? So this is what I meant. So now let us come back to our original slide. So this is what I meant. So normally your 3 degree of freedom spatial robot was something like this. So the first link had a motion like this. The second one can go like this. The third one can go take it further like this, so that first vertical axis can rotate whole of the plane containing the 2R manipulator along. Okay, let me just show you the kind of motion it can make again. So you see the robot, if it moves, it can move like this. If it doesn't rotate its first joint, so rest of the two joint can make it move in a plane. Say it is something like this, so it becomes very easy to visualize this. So let us say it is in this configuration when second and third link has already attained some angle and this is there in a plane. Okay. Now if I move it, it can make motion something like this. Got it? So to make things very simple, what we can do, we can make this frame, the ground frame, situated over here. So I can quickly make the offset, first offset like this. Okay. So this robot is now like this. Got it? So now if I say to move, it can go move like this. Got it? So this is your special 3R manipulator that you have seen earlier also. Okay. But you have some offset which is over here, that was the link length. Okay. So moving ahead further. So this was your standard 3R manipulator. Got it? So this is how we have reached till here. This is the effective DH parameter for that. So this was vertical theta 1, this is theta 2, this was theta 3. This is a standard manipulator. But if you look carefully, your robot, it has first link, which is here. Okay, the shape of that is something like this. Second link is from here till here, whereas the third link has got a very different shape. It is something like this till the wrist center point. Okay, so it has to contain the dimension which makes it something like this. Got it? So this is what I am trying to make. So this was your standard 3R manipulator, but I don't want to continue with this. I want to make it very similar to the first 3 links of my Yaskawa GP12 robot arm. Okay, so this is how it is. So now I have made it in a way that it can take up this dimension that is over here, this dimension which is like this, and there are 2 dimensions which are here, that is 200, so it comes here, and 640 mm over here. Now it is this. Now it has reached till the end effector. For 3R it is the end effector, but actually after that also it continues further till the tip. After this is spherical wrist. So for 3R this is the end effector, otherwise it is wrist. Got it? So now can I do inverse kinematics using our standard 3R special robotic arm? So let us do that. So now I'll try to consider that on this. So why you cannot take this in a standard DH parameter is that in DH parameter you can have displacement along x-axis. So this is your x-axis, and distance between two z, this becomes the link length. Again you have another z which is situated over here. Okay, you can move in this direction, that is from here till here. Okay, that is by 640 mm, but you cannot move along y-axis. So where is your y-axis? This is your y-axis. You cannot make it move like that. Okay, you cannot have a DH parameter that can take care of this. So what we can do here, we can replace this the way it is shown in the next figure. So instead of making this link like this, 200 and 640 like this, I can create an effective distance link which can take me to the same point. It is the end effector. I am only talking about the end effector position, not the orientation. Orientation definitely will change, but yes, if I talk about the end effector position, so you reach to the same place. Now my link is something like this. So it takes me from this to this with a new length, that is squaring and adding, taking the root, bring it to 670.522. So this is my new link. Okay, that moves between two z-axes. One of the z-axis is here, other one is here. So it is moving along x-axis like this. So new length is 670 and there is no 200 and 600 distance. There is just one link length, that is 670, and it can be put in a DH parameter. With the initial joint angle, this time if at all you have a joint angle that measures from this horizontal reference, okay, so it has already moved by an angle 17.354. So this I call it as alpha. Okay, so this is theta 3. By default we used to call it theta 3. Now we'll call it theta 3 alpha. That means theta 3 plus alpha. So when theta 3 is 0 degree, it has already having some angle that is 17.354 degree. Okay, that is simple trigonometry, I can find it out. So in case of Yaskawa, it measures theta 3 like this, from this vertical to this. Got it? So if at all it is moving like this, so this is theta 3. If I have to make it move this way from here, this our own reference frame, so this is your new theta 3. So effective theta 3, if it moves by theta 3, will be theta 3 plus this alpha. So we call it theta 3 alpha. So now the new angle, if this link, the third link, moves by an angle theta 3, the total angle with standard DH is theta 3 plus alpha. Got it? This can be taken care by having a DH parameter which is like this. And with respect to Yaskawa, it is something like this. So if you measure it with this reference frame, it is like this. Okay. So when Yaskawa shows 0 degree, that means this link gets aligned to this. So our actual link, new link, has already rotated by minus 72.646 degree. Okay. Got it? So our new robot is like this with link length 670.522 mm. Got it? It has already moved by an angle 17.354 degrees. Okay. So that is my new robot. Rest everything remains the same. So now I will solve inverse kinematics problem. This is my robot. I want to solve inverse kinematics for this. So x, y, z can be straight away obtained from the forward kinematics equation. Only thing that has changed is the angle, that is theta 3, becomes theta 3 plus alpha. Because you know this link has already rotated by some angle, that is alpha. This one. Got it? So that angle is considered here. Rest everything is same. This time you also have A1, that is A1, as compared to our previous 3R special manipulator that we have done. Okay. Now I'll solve for this. Okay. So for GP12, D1 is equal to 0. Where is your D1? D1 was taking it to this. This was your D1. This becomes equal to 0, and I placed my first frame over here, that is attached to the ground. Okay. So using first two equations, I can quickly obtain theta 1. So theta 1 is this. Done. And Ex dash is x by cos theta 1 minus A1. Ez dash is equal to z minus d1. Z minus d1. So this is your Ez dash. Got it? Now I'll move ahead. I have created these two equations. Okay. This is very much like 2R manipulator, planar manipulator. So you can solve it. You can directly see the 2R manipulator subset which is here, and on that plane, which is a plane of x dash and z dash. Got it? X dash and z dash. Okay. You can solve it and you can quickly obtain your this, where 3 alpha, you know it is theta 3 plus alpha. Got it? So exactly copying your 2R manipulator solution, this takes you to theta 3 and theta 2. That can be easily solved. Theta 1 was solved here. Theta 1 was here. So now you have theta 2 and 3. So this is solved exactly like your 3R special manipulator with little bit of changes to that, so that you can consider the pre-angle 17 point, whatever angle you had, that is for alpha. So that angle is already considered here, and rest everything remained the same. So now you can obtain the angles for Yaskawa robot. So this is your Yaskawa robot. Now if you know the wrist center point location, you can calculate all the angles theta 1, theta 2 and theta 3. Got it? So you have done inverse kinematics up till this point. Got it? So moving ahead, let me take the whole robot now. This is a sample set for which I have solved it for this configuration, where you have x is equal to 795 for this, y is equal to 0 and 1264 mm for this along z. Got it? So this is the coordinate which is given for the wrist center point. Okay. I have just verified that using this MATLAB code which is here. Okay. This gives me this. That is the correct solution for this, which is quickly visible also. So this is how this 3R for Yaskawa GP12 till here is solved. Okay. So this was the positioning part of my Yaskawa GP12 robot. Okay. Now I'll do the wrist partitioning method and segregate this robot into two halves. First part will be till here, that is the positioning part. Next part, that is this after the wrist, is orienting robot. Got it? So I'll just change it. So normally kinematic decoupling can be done even with any standard industrial robot. So you see it has first three link, which is like a standard spatial 3R manipulator. This was vertical axis which can go like this. Then you have one axis that can make it move like this. Another axis which is here that can make it move like this. And finally you reach till the wrist center point. Same for this. This is KUKA robot. This is Yaskawa robot. Okay. Again, you to reach till here, that is the wrist center point, you have first vertical axis with some offset here, and then you have two distances, this one and this one. Got it? So you have first axis that can move like this, second axis which can make it move like about this, and third axis which is like this. After that you reach till wrist center point. Okay, so positioning workspace is very, very clear. Now let us look the orienting link. So last link which is here after that, okay, this one for this, and here you see this one. So that is the orienting link. So after the wrist you have another three intersecting axes that makes it a spherical wrist, that is here. Okay, so this is your actual Yaskawa GP12 robot, in which you have seen you have third link which is shaped like this, and you know you have already solved for that. So you have one axis which is like this, you have another axis which is making it like this, you have first axis which was vertical, you know, so that used to rotate it like this. So this is how it is. So till here it is 3R special manipulator, the modified one that we have discussed today. Okay, so this is how you reach till this, and after that you have the orienting link. So this is the link D6 that we initially had when we discussed DS parameter of any 6 degrees of freedom special robot. Okay, so this is the distance. So you have inverse orientation wrist kinematics that is accounted over here. Positioning kinematics is accounted till the first three links. So this is how it is decoupled. Let us work it out. So yes, the first step that you know for this kind of robot is you know the end effector position. end effector position, that is the position vector, this one. I'll just draw it over here. This is the location that you already know. That means you know this vector from frame 0 to frame 6 given by O, that is the position vector here. Got it? So this is well known. You also know the orientation of the end effector. That means you know the frame which is attached to the sixth link. Got it? So you know the orientation matrix for that. Okay? Because you know the roll pitch yaw of your last link, that means you know the orientation of the last link. How you know? Convert the roll pitch yaw angles. Normally your industrial robots will tell you roll pitch and yaw angle with respect to the base, that is with respect to 0. So you have to convert that to the rotation matrix. You can quickly do it using RPY transformation matrix that we have studied. So you can use this and you can get to this. So this is how you can obtain rotation matrix 0R6. You already know this. You have inputs that are given here, that is OR6, and roll pitch yaw angle was given. You have converted it to rotation matrix. Got it? So these are the two information that you have acquired from the given one. Okay. Now moving ahead, you have this now. You have converted RPY to rotation matrix. You have this. Okay. Now you have to solve for the first three joint variables, theta 1, theta 2 and theta 3. You already know this. Okay. This vector is known. Okay. This distance was known. This distance, which is from the wrist center point, to this distance, is well known. Through your robot data sheet, you can just take out that distance, that is D6. As per DH, it comes out to be D6. You already know the orientation of your last frame, that is 0R6 is known. You have to multiply the vector 0, 0, D6, and what do you get? You get this vector. This vector is obtained. Got it? So once you obtain this vector, you can quickly obtain the wrist center point vector. That is the vector which starts from the origin and till here. This is your wrist center point. Got it? That is this C point. Got it? So this is easily obtainable using vector triangle. So instead of writing 0, 0, D6, you can take out the D6 and write like 0, 0, 1. Your matrix goes here. That is okay. So this is your vector which is here. Got it? So this vector, and you already have this vector, so you can calculate this. So this is your first step when you have calculated the wrist center point. So this point. So once you have obtained this point, you can calculate rest of the three joint angles. The first three joint angles, theta 1, theta 2 and theta 3, using the techniques that we have learned today. That is the modified 3R special manipulator. Earlier we did it for 3R regular manipulator. So both are applicable for different kinds of robot that we have seen in our first slides. Okay. So this is all. So now you already know these and first three joint angles. So if first three joint angles are known, you know theta 1, you know theta 2, you know theta 3, and you already know the informations that was D1, A2 and A3. Those were the distances. So you can quickly do forward kinematics and you can obtain this frame. Okay. This frame means you can do forward kinematics, multiply 0A1, 1A2. These are the link transformation matrix. And finally what you get? It is 0T3. So what is this? This has the position of this frame, position of the frame that goes here, and this is your rotation. Got it? So this is how you can obtain 0R3. So this part is 0 2R3. This is your position. That is already you know it is this position. Got it? So once you know your joint angles theta 1, theta 2, theta 3, you can calculate the rotation matrix for this. This is your transformation matrix, homogeneous transformation matrix that has parts of this point C. This was your C. Okay. And you also have rotation matrix. This parts that shows the 0R3, which is very much required for rest of the inverse kinematics problem that we will be doing. So we have obtained 0R3 using first three joint angles using forward kinematics. Okay, so this is step 3. So now step 4. So you already have all these values. So 0R3 when taken as a product from 3R6, it will give you 0R6. 0R6 is already known. You already know the end effector orientation with respect to the base that we did quite earlier, because that is the input from roll, pitch, yaw angle. You converted this directly. Okay, so this is known. This is just now we came to know using first three joint angles. So I have just taken inverse of that to find out this one. So this is found out using this relation. Okay, so you just take inverse of this and take it to other side of this. So you can take this. So inverse of rotation matrix can be quickly obtained by taking the transpose, you know. So it is this. So now what I have obtained is 3R6. That is transformation matrix from this to end effector. Not the complete transformation matrix. So we already know that because we know D6. But still what I need now is only this, that is 3R6. That is rotation matrix from frame 3 to frame 6. Got it? So this was your 0, this is 1, this is 2, this is 3. So from 3 to 6, you know, is here. Got it? So this is your orientation matrix. That is what you know with respect to third frame. Recall the forward kinematics of a spherical wrist that we have done using Z, phi, W Euler angle. Okay, you had yaw angle, you have pitch angle, you have roll angle. This can be arranged in a straight line. So if you know last three joint angles, theta 4, theta 5 and theta 6, you know that is a spherical wrist. So you can directly write that transformation matrix like this, and including the distance D6, it becomes this. Got it? And this is your Euler angle transformation for the same. You can obtain that using ZVW Euler angle. Okay, that we have studied very much in the beginning. In terms of variable, it has theta 4, it has theta 5, it has theta 6. This is your rotation matrix. Okay, that is from 3 to 6. So that is here. Is it not? So I can write it like this. So this part as a submatrix is here. Okay, remaining is like this and can be extracted out. This is exactly this center matrix 3 cross 3, that is here. Got it? If you want to see it clearly, I'll just vanish. So this is it. As we have discussed in the step 4, we obtained 3R6 with some values. Now we have in terms of variables, that is using matrix for spherical wrist. Just previous slide we saw this. Earlier we have already obtained this. Okay, now equating both of this, you can extract the informations. Okay, the first one, you see theta 4 can be obtained from Q23 and Q13. See the last column, this one, this two, So if you divide these two, you can quickly get this by this is equal to tan theta 4 is equal to whatever are the values which are here. You can take arc tangent solution and you can obtain theta 4. Got it? Similarly, theta 5 can be obtained. If you can see it clearly, it is 1 3 and 2 3 and 3 3. 3 3 is this one, this and this, squaring, adding and taking the root. What you can extract is sine theta 5. Sine theta 5 is can be directly extracted. So cos square theta 6 plus sine square theta 6 will go to 1, and finally you will be left with sine square theta 5 taking root, it is sine theta 5. So sine theta 5 comes here and cos theta 5 comes here. Okay, and that is what will give you theta 5. Got it? So that is how you obtain theta 5. Now the angles theta 6, that is obtained using 3 2 and 3 1. Again you have similar two values that are to be used, 3 2 and 3 1. You just see where it is, 3 2 and 3 1. So these are the two. Okay, just use them. Okay, you divide this by this, what you will get, sine theta 6 by cosine theta 6. So it is tan theta 6, arc tangent of that will give you this. But this has some limitation. It can vary only theta 5 from 0 to pi. Alternate solution is theta 4. When theta 4 is 180 degree apart, that means you have alternate solution. How is it possible? Let me just show you using this model. Okay, what do you see here is first solution that can take you to, so let us see this point. Okay, same thing can be obtained if you rotate theta 4 like 180 degree apart and bring it down like this, and you reach to the same place. Got it? So if it is at this orientation, same orientation can be obtained by rotating theta 4 by 180 degree and bring it theta 5 like this, and you reach to the same orientation. So that is what it is meant here. Okay, so you reach till this. So this is the alternate solution for that. That will give you theta 6. So you have obtained theta 4, theta 5 and theta 6. Theta 1, 2 and 3 was obtained earlier using inverse kinematics of 3R special manipulator subsystem which was there. Once you knew the spherical wrist center point. Okay, so theta 1, 2, 3 was obtained. 4, 5, 6 is obtained here. Got it? So you see it has two solutions at least. Okay, so overall, this type of robot has got 8 solutions, at least for this structure that I have. So yes, that's all for this lecture. So in the next lecture, we'll see robot Jacobian. Okay, that will relate the end effector rates to the joint rates. We'll talk about motion. We'll try to find out the acceleration. We'll try to find out the velocities, provided I know the joint rates. Okay, we'll discuss something which is known as singularity. Once we'll discuss Jacobian, that is the rate relationship. Okay, that's all for today. See you then. Bye-bye.